This video is going to provide a bit of an introduction to matrices as they're used in maths, provide some basic concepts and notation, and a couple of the basic operations that we use with matrices as well. So what is a matrix? Well, a matrix is defined as a rectangular array of numbers, and I guess we can think of the word array here in a similar way to the word arrangement. So a rectangular arrangement of numbers, which means we can think of it quite like a table where numbers are arranged in rows and columns. So here's an example, a matrix with the name A, which is equal to this arrangement of numbers. So notice the similarity to a table. We've got, or maybe a spreadsheet, we've almost got cells that are arranged in rows down the page and columns across the page. There are some obvious differences with tables. The way that we write a matrix doesn't have headings for rows and columns, and rather than lines within the table, it's just got brackets. Those brackets can be square brackets like we've got on this one. Sometimes you'll see them with curved brackets as well. So we need to be clear on which are the rows and which are the columns. So the rows are the ones which run across, or the numbers in the rows, I should say, run across. So rows actually kind of go down the page in the sense that row 1 is the top row on the page or on the matrix, row 2 below that, row 3 below that, and columns run, I guess, like columns in a building, or maybe the columns that hold up a bridge or something like that. So columns are vertical and rows are horizontal. And we can describe a matrix in terms of its size or its order or dimensions. So we can say a matrix has size or order or dimensions. These are all sort of interchangeable words here. And we say its dimensions or its size are m by n. Maybe let me grab the colors actually that correspond to what I've done there. So m is the number of rows and n is going to be the number of columns. So in our example there, we could say A has size. So as we go down the page, there are 3 rows, and as we go across, there are 4 columns. So that particular matrix A is a 3 by 4 matrix. And we can refer then to individual entries or elements within that matrix. So how do we refer to those? So we can refer to those by using a letter, a lowercase letter, which corresponds to the uppercase name of the matrix. So in this case I'd be using a lowercase a because my matrix is called A, and then a subscript I and J, where I would be the row number and J would be the column number. So a little bit like map references or maybe even spreadsheet cell references. So for example, let's consider the matrix above. If I said A subscript 1 3, so A1 3, that's saying in row 1 go across to column 3. So row 1 column 3, let's grab a highlighter, pick that one out. There's row 1 column 3, that is equal to 2. Let's do another one. Let's go row 3 column 2, so down to the 3rd row and across to the 2nd column. So that one there is equal to 3, and so on. Notice that the entries, that every spot has to have a number in it. There can be zeros. So perhaps if this is representing something where the numbers actually sort of mean some physical quantity, we might have to put some zeros in there where there's no quantity. In that matrix, as in lots of the matrices that we'll deal with, there'll be integer values. They can be positive, negative, but they can be any value at all. They can be decimal, rational, irrational, surds, whatever. That doesn't matter at all. All right, so let's think about some of the other sort of properties of matrices. So firstly, we're going to say that two matrices are equal. So let's think about what it means for equality of matrices. So two matrices are equal if and only if, there's that phrase again, if and only if they have the same dimensions or matching size. So they are the same size and they have equal values in every corresponding entry, and have equal values in all corresponding entries. So we can't just say they're equal if they're both, 3 by 4 matrices. They have to actually have equal entries. So let's try and write that a little bit sort of in a mathematical statement. So we could say matrix A equals matrix B. Remember our symbol for if and only if, we can use the double-headed arrow, the implication each way. So we'll say entry Aij has to equal entry Bij for all I and j. So remember, I here is representing the row number and j is representing the column number. So that might sound pretty straightforward, pretty logical, but we actually use that quite a bit in working with matrices. So here's a really simple example. Let's say I had one matrix, we'll just go at 2 by 2, so it was 2x, maybe -3 and 5, and let's go a second matrix here, B, we'll call it 2, 1, y, and 5. Now you can see in a couple of positions or entries there we've got values that are equal. So these two matrices, if they're equal, then that implies that x has to equal 1, because that's its value in the corresponding entry in B, and y would have to equal -3, because that's the corresponding value between the two matrices. And we could make it a double-headed implication and say if x is equal to 1 and y is equal to -3, then it follows that matrix A has to equal matrix B. So that's where we'll use that property of equality often when we're sort of solving things to do with matrices. All right, let's talk then a little bit about the property of addition or the operation, I should say, of addition and subtraction. So two matrices can only be added or subtracted. Give that a little underline since we're talking now about the operation of addition and subtraction. Can only happen if they are the same size. So straight away we can't add or subtract matrices that are of different dimensions. Let's do an example here. So let's make what do I make it, a 3 by 2, so -4 and 7. We'll just whack some values in here. 2, -1 and 1, 3. So notice again I'm using all integers, but as I said before, certainly matrices don't have to be only integer values. Now we'll make B the same size so that we can add and subtract these. So let's say 3, -2, 4, 0, 1, 5. Then A plus B. Well, let me put in a line of working out for this one here. So -4 plus 3. So we're just adding entries in corresponding positions. 7 plus -2. Let me do a highlighter for one of these. So now we're into this one here plus this one here. So it's going to be 2 plus 4 over to row 2, column 2, -1 plus 0. Row 3, column 1, 1 plus 1. And 3 plus 5. So what's that equal to? -4 plus 3 is -1. 5, 6, negative 1, 2, and 8. So that's the result of adding those two matrices. What about if I went B minus A? Now I might just write in the result here, so I'm doing B minus A. I won't have space to do in the working as well, but B, that means I'd be taking 3 and subtracting negative 4 for the first one. So 3 take away negative 4 would be 7. Negative 2 minus 7, negative 9. 4 minus 2 is 2. 0 minus negative 1 is 1. 1 minus 1 is 0. And 5 minus 3 is 2. So take a moment just to pause if you want to work through that. Alright, last thing in this video, the other property we'll consider is scalar multiplication. So we'll go on to matrix multiplication in a subsequent video. So for scalar multiplication, we're familiar with this concept from working with vectors. Alright, so for scalar multiplication, which is where we're taking a matrix and multiplying it by a scalar value, k, or some real number, every entry or every element gets multiplied. Every entry is multiplied. I guess it's kind of saying it's scaled by that, isn't it? Multiplied or scaled by that factor. Okay, so everything's being scaled up or down by that factor of k. Let's do an example. We'll use the matrices from before, so these A and B matrices from up here. So let's say I went, using previous matrices A and B. So what if I just went something like 2A minus 3B? Okay, so popping up here, what was A was equal to, let's write it in here, negative 4, 7, 2, negative 1, and 1, 3. And we're going to subtract 3 times matrix B, which is 3, negative 2, 4, 0, 1, 5. Okay, so let's do some working out for this one here. So maybe I'll do one line of working. So 2 times negative 4 is negative 8, minus 3 times 3, which is 9. Then we've got 14, and then minus 3 times negative 2 will be plus 6. I'll have 4 minus 12. I'll have negative 2 minus 0. 2 times 1 is 2, minus 3. 2 times 3 is 6, minus 15. So that is equal to negative 17, 20, negative 8, negative 2, negative 1, and negative 9. Alright, so there's a few of the basic concepts and operations for working with matrices.